So welcome to ATMOS 2750, day number 15. Today we're going to start off with talking about nuclear power, and then we'll look at renewable energy sources, specifically hydro, wind, solar, and geothermal. And lastly, and probably most importantly, we're going to do a cost comparison of the electricity generation methods to see if renewable energy sources are becoming competitive with traditional fossil fuel-based electricity generation. So if we look at the location of nuclear power plants in the United States, you'll see that most of the nuclear power plants are actually in the east. And there's a reason for that. And the reason for that is that most of the population of the United States is east of the Mississippi. And you want to generate the electricity close to where it's actually used because you end up losing a lot of the energy during long-range transmission. So you'd think, well, maybe you want to put a lot of nuclear power plants in the middle of Wyoming and then transmit the power, but that's not an efficient way to do that because of the loss of energy along the way. And you'll notice that there are no nuclear power plants in the Intermountain West. There are a couple in California, a couple down in Arizona, and one in Washington, and that's it in the western U.S., west of the Rockies. And I read this week that the Diablo Canyon nuclear power plant in California is slated to be shut down in 2025, even though the power plant still has years of life left. California seems to be moving away from nuclear and more towards traditional renewables. If we look around the world, you can see that we have power plants obviously in the North America in the United States, but Europe is also heavily invested in nuclear, as is Japan. And China has started building nuclear power plants as well, which aren't reflected in this particular map. So here you can see that the United States by far produces the most nuclear energy of any country in the world. France is a distant second. This data is a little bit old, and China has significantly increased its nuclear capacity. China is now, I believe, the number 3 country in the world in terms of the amount of energy, which is electricity, which is generated through nuclear. However, if you translate that into the percent of the energy reliance upon nuclear power, you'll see that France is number 1 in the world with almost 80% of their electricity generation being nuclear. The United States is down around 20%. So how does a nuclear power plant work? If you want to learn more about nuclear fission, I encourage you to watch this YouTube video. It'll talk about the fuel rods in the nuclear reactor and the importance of the containment rods to moderate and to control the amount of fission that's going on in the reactor core. But once you realize that the reactor core is just a way to heat water, then the performance of a nuclear reactor is exactly the same as the coal-fired power plant and the natural gas power plant. You basically heat water, you flash it to steam, you use that phase change in order to drive a turbine. And the nuclear power plant does the exact same thing. It has a closed loop. So the water that's inside the nuclear reactor cycles in and cycles back to the nuclear reactor, and then they have cooling flow, which is an open system, which brings in water from the environment, cools the condenses the water back, and then is put back into the environment at a higher temperature. The main issue with nuclear power, however, is what to do with the waste that's generated during the process. And many people are concerned about that, and the used nuclear fuel rods are these ceramic pellets that are encased in these metal tubes, and they are highly radioactive, and so they need to be shielded and stored away from population centers. And so the current process is that these nuclear fuel rods, these spent rods, are being stored on site in very large bodies of water, kind of like extensively large swimming pools. And the water absorbs much of the heat and radiation that's being given off by these fuel rods. However, that's not a long-term solution. Because these fuel rods are going to remain highly radioactive for 100,000 years or more. And so we need to be able to find a long-term storage where we can tuck them safely away from humans and do it for 100,000 years or more. So one potential long-term solution is Yucca Mountain in Nevada. Let's take a look at that site and see what it has going for it. So the Yucca Mountain site is located about 150 miles northwest of Las Vegas. It happens to be in an area that's sparsely populated, and it is one of the driest areas of the United States. The area is shielded from precipitation by the Sierra Nevada mountains in California, and so much of the precipitation and much of the water is removed from the atmosphere before it makes over those mountains. It is a relatively geologically stable area. It's not prone to really large earthquakes, and it is there's a large excavation that's already occurred inside Yucca Mountain, and it has a capacity to store all of the nation's waste. So why haven't we started using it? I'll give you two words, basically one person, Senator Harry Reid. He decided that he was a senator from Nevada, and he decided that nuclear waste was not going to be deposited in his state. And he was very powerful, and he prevented every opportunity he had to be able to prevent the waste from being transported there, and it still has not been approved for long-term storage. Now, Yucca Mountain is not the only potential long-term storage site that's available. Others have been viewed as well, have been reviewed. One of the ones that seems to show promise is in my home state of Kansas. There are salt mines that are located about 700 to 1,000 feet below the Earth's surface in a thick layer of salt that was deposited several 100 million years ago when Kansas was a shallow sea. And these mines are located well below the water table, and so they're extremely dry. You can't have salt in the bedrock with water because the water would dissolve the salt. So it's obviously very dry. It's been that way for hundreds of millions of years, and Kansas is not prone to earthquakes as well. So it seems like a potential reservoir for putting in the high-level nuclear waste, because there are literally miles and miles of tunnels that have been drilled through the salt over the years. So let's take a look at Utah's renewable energy mix. Right now we have 25% of our energy, renewable energy, is being generated by solar, followed by wind at 19% and hydro at 19%, 13% geothermal, 11% home solar, and 13% biomass. I recall that biomass is conversion of plant material into fuels, which are then combusted for energy. So this pie that we have here for showing the mix of solar and wind and other renewables, solar is growing rapidly in the state of Utah and will soon become the dominant source. So how does solar energy work? Well, I encourage you to watch this YouTube video that will walk through the process by which photovoltaic cells convert solar energy into electrical energy. And I want to just mention three things. One is that the raw materials for solar photovoltaic cells is actually quite cheap. It's silicon. Silicon is one of the most abundant elements in the Earth's crust. Number two is that the efficiency of these solar cells has gone up significantly over time, but it's still about 20% efficient. So it can only convert about 20% of the incoming solar radiation to electricity. But that's up significantly from what it used to be. And lastly, the reason why photovoltaic cells have traditionally been fairly expensive is because the manufacturing of the photovoltaic cells has been expensive. And as companies have worked to develop better manufacturing processes, that expense has been coming down, and we'll see the net impact of that later on at the end of today's presentation. So not all areas are really suitable for solar power production. Here we have a map showing the average annual amount of energy that's available for solar power. And you can see that the southwestern United States is kind of an ideal location for solar power, as is much of the southeastern part of the United States as well. There are some places where solar energy would be a challenge. That would be the Pacific Northwest and the extreme northeastern parts of the United States. If we look at the amount of solar power that's being generated, there's a significant trend. It's a very steep rise in the amount of solar that's being installed in Utah. 10 years ago, it was almost negligible, but it's been increasing at an almost logarithmic rate. Let's take a look at that. So here you can see that logarithmic growth in the Utah solar power generation. Year over year, it's essentially kind of a straight line on this logarithmic plot, which indicates a very fast growth rate. So how does a wind turbine work? So here I encourage you to look at this YouTube video, which describes how a wind turbine converts the kinetic energy of the wind into a electrical power through the use of a turbine. So here you can see the potential for the wind power is not uniform across the United States. So the green here has relatively low potential for wind power, and the oranges and reds and purples are areas that have high potential for generation of power by wind. And you can see that the dominant locations for wind power are the middle part of the United States, just east of the Rocky Mountains, all the way from Texas, all the way up into North and South Dakota and into eastern Montana. But of all the states, Texas and Wyoming have the most potential for wind power. Utah, if you take a look, is not particularly well situated for wind power, although it is much better than the eastern part of the United States. So in Utah, one of the things that they've done to encourage the construction of wind power is to offer residents of Utah a voluntary way that they can actually purchase wind power. It's called the Blue Sky Program, and it's offered by Rocky Mountain Power. And what it does is it sells blocks of electricity generated by wind power in 100 kilowatt hour blocks. And so at my house, I use 600 kilowatt hours of energy per month, and I actually purchase 6 of these blocks so that I buy an equivalent amount of electricity from a renewable resource to kind of offset my own personal use. And each one of those blocks costs about $6, so I pay an extra $36 a month on my electricity bill in order to ensure that there's enough, to ensure that I'm getting enough renewable energy into the system to account for my own personal use. And this money is used to invest in new wind power, and a lot of those investments have been in adjacent states. So primarily in Idaho and Wyoming, Oregon, and Washington. So as of 2017, we can see that the wind power capacity is primarily dominated by Texas, with over 22,000 megawatts of power, wind power installed. And in the central part of the United States, Kansas, Oklahoma also have quite a bit, as they do in the western west coast as well, Washington, Oregon, and California. Utah itself has very little, only 391 megawatts of installed power as of 2017. And you'll see that in the southeastern United States, they do not have much wind power installed at all. In part, that's because of the low wind potential, but also the damage that can occur associated with hurricanes. You don't want to have one of these wind turbines in an area that's going to be struck by a hurricane. It'll do a lot of damage to the infrastructure. So hydropower I encourage you to watch this little YouTube video, which will demonstrate how hydro converts potential energy into electrical energy. And it just basically uses the elevation difference of the water to let the water fall and turn a turbine, which then generates the electricity. So hydropower plants in Utah, there are 29 hydropower plants, but only 7 of them generate any significant amount of electricity. So the total capacity is about 1,684 megawatts, and by far the dominant one is Flaming Gorge Reservoir, which generates almost 1,100 megawatts by itself, which is about 2/3 of the hydropower in Utah. Lastly, we have geothermal, and geothermal energy makes use of the heat in the ground that's naturally occurring. I encourage you to watch this YouTube video on how geothermal power works. But there are the 2 types of systems. We have the closed system and we have the open system. The closed system will inject a fluid into the earth that will then be heated, and then they can bring it back to the surface, flash it to steam to turn a turbine, and then condense it and send it back down in a closed cycle. A closed cycle essentially has 0 emissions. And then there's the open cycle where they pump hot water out of the ground, flash it to steam, and then use that to generate the electricity. And that does have emissions to the atmosphere from whatever was in the water that they're pumping out. If we look at the geothermal power potential across the United States, you'll see that the western United States, specifically the Intermountain West, has a very high geothermal power potential. It's an underutilized resource in the West. California has the first and largest geothermal power plant, but Utah only has 2, and we'll talk about that here in a sec. So Utah has 2 geothermal plants, only totaling 54 megawatts amongst them. One's near Milford, one's near Cove Fort, and these are mostly identified as pilot scale projects to do a proof of principle, so that they could show that you can in fact generate electricity through geothermal here in Utah. So let's look at a cost comparison. So I'm going to start off with data from 10 years ago. So this is from 2011. And in 2011, the most expensive type of energy was solar, at about 7.7 cents per kilowatt hour. The cheapest was hydro and nuclear. And then you have coal and gas, which are about 4.5 and 5.5 cents per kilowatt hour. And wind is kind of in between coal and gas at the time 10 years ago. So what's happened during that time period? Well, there's been a lot of regulation that's been put on the nuclear industry, which has raised the price of nuclear. Hydro has stayed essentially constant. The natural gas costs have dropped below that of coal, and mainly because the price of coal-generated electricity has gone up because of the additional pollution controls that have been mandated, mainly removing particles from the effluent, removing mercury from the effluent, and making sure that they remove sulfur dioxide and nitrogen oxides from the effluent before it's put into the atmosphere. And those have driven coal prices up. In the meantime, the mass production of wind and solar facilities have actually brought those prices way down. So let's flash forward to the current situation. So on the previous slide, we saw what the cost was for electricity generated by different methodologies back in 2011. And now I'd like to contrast that with the costs associated with that as of 2020. And that's what the dark blue bars are. So we can see that coal has become much more expensive than it was 10 years ago. And that's primarily due to environmental regulations which require them to remove additional pollutants from the smokestacks. So now they, in addition to removing NOx and SO2, they also have to remove mercury from the effluent as well. Natural gas has become slightly cheaper over time. primarily due to the fact that there are more natural gas plants being built and that there's an economy of scales. With nuclear, nuclear has become much more expensive over the last 10 years, primarily due to enhanced safety regulations after the Fukushima disaster in Japan. And there's also the fact that many of the nuclear power plants are being decommissioned, and those costs still factor into nuclear power, even though they're not actually producing nuclear power. Wind power has gotten slightly cheaper due to economies of scale. The more facilities that you build, the more manufacturing that's going on, the cheaper that you can do it. Hydro hasn't changed much, and the big mover over the last 10 years has been solar power. Solar power has basically decreased by about 50%, and that's primarily due to research and development that was conducted in China trying to improve the efficiency of solar panels and to improve the manufacturing process in order to bring down costs. This has also been a move away from residential solar to commercial scale solar projects, which have an economy of scale, which also further reduces the cost associated with solar. And as it turns out right now, wind and solar are two renewables, and they happen to be the cheapest way to generate electricity as of 2020. So here you can see that nuclear is now the most expensive of these particular types of energy, and this the y-axis is dollars per megawatt hour, which is, if you divide by essentially kind of 100, we'll get to cents per kilowatt hour. So the nuclear is about 8 cents per kilowatt hour. And then after that, the next most expensive is coal, which is about 7 cents per kilowatt hour. And a lot of our energy is being generated by natural gas now, and natural gas is about 4.2 cents per kilowatt hour. And you'll see that wind, onshore wind, is now cheaper than the fossil fuel alternatives of natural gas and coal at about 4 cents per kilowatt hour. And solar is not quite cheaper than the natural gas yet, but the trajectory that it's on means that over the next decade or so, solar will become cheaper than the traditional natural gas-fired power plants as well. And at that point, there will be an economic incentive to switch to renewables because they provide you the cheapest form of energy as well. So that change is happening, and that will have a rather large impact on the market for new types of power generation in the United States and beyond.